Welcome to question 8 of the 2012 Mathematical Methods Exam 1. In this video we will be looking at the solution and examination advice for this question. A reminder that this video is in no way endorsed by VCAA. For part A, we have the random variable x is normally distributed with a mean of 100 and a standard deviation of 4. If the probability x is less than 106 equals q, find the probability that x is between 94 and 100 in terms of q. So to start this question, we're going to draw a bell-shaped curve to represent the normal distribution. So it would look something like that, with x being normally distributed with a mean of 100 and a variance of 4 squared, or the standard deviation squared. So the 100 is this mean value here, which is centered in this bell-shaped distribution, and then this would be 104 and this would be 108. And we know that the probability that x is less than 106 is equal to q. So 106 is here, and the probability of it being less than 106 is this shaded region. So we know that that area there is q. That also means that this area up here in the tail on the right hand side of the diagram is 1 subtract q. Next we need to actually find the probability that x is between 94 and 100 in terms of q. So we're going to draw a second bell-shaped distribution directly underneath, and this is still x with a mean of 100 and a standard deviation of 4, so this will be 96 and this will be 92. And we are asked for the probability of x between 94, which is here, and 100, so that's this region just here. And by symmetry of the graph, we know that this green shaded area here is equal to 1 minus q. And we also know that half the probability lies above the mean, so this is 0.5. So with all that in mind, we can now find the probability that x is between 94 and 100 as being equal to, and now the whole bell-shaped distribution has an area of 1 underneath it, and if we subtract off the 0.5 in red, we're just left with a half, so that represents all of the green and the blue region. However, we just want the blue region, so we're going to subtract away the area of the green region, which is 1 minus q. And now simplifying this, we'll have a half subtract 1 gives negative a half, and then we'll have subtract negative q, which gives positive q. So that is the answer to part A of this question. So from the examiner's report, we can see that 34% of students got this question fully correct, and that overall the question appeared to confuse many students. There were many unsuccessful attempts to allocate an area to the 1.5 standard deviations above or below the mean, but that was not possible without the aid of a CAS calculator, which is not allowed for this exam. And those that were most successful with this problem drew a diagram and realised the symmetry that applied to this question. For part B, we have the probability density function f of a random variable x is given by f of x equals the linear equation x plus 1 over 12 between 0 and 4, and that it is 0 otherwise. And we are asked to find the value of b such that the probability that x is less than b is equal to 5 on 8. So unless it's ridiculous to do so, it's often useful to draw a graph of the probability distribution function. So if we sub 0 into our rule, we get 0 plus 1 is 1 over 12. So at this point here, we have a point 0, 1 over 12. And it's a straight line with a positive gradient. And now if we substitute 4 in, we get 5 over 12 as the y value. So this would be the point 4, 5 over 12. And then it would be 0 otherwise, so we'd have these regions on the graph as well. And that's at 4 and that's at 0. And now we want to find the value of b such that the probability that x is less than b is equal to 5 on 8. So there must be some value b here, so that the area under that curve is equal to 5 on 8. So that area is 5 on 8. So now that we've set up the question, we can use an integral to solve this problem. So we know the integral between 0 and b of x plus 1 over 12. So the over 12 is just a constant that I can take out the front as 1 over 12, so we'd just have x plus 1 behind. So the integral of x plus 1 dx between 0 and b is equal to 5 over 8. Next, we can find the antiderivative of x plus 1, so we're going to have 1 over 12 multiplied by, and the antiderivative of x is x squared over 2, plus the antiderivative of 1 is simply x, and that is between 0 and b, and we know that that is equal to 5 over 8. And now if we were to multiply by 12, we'd end up with 60 on 8, which is simply 15 on 2. So that is going to equal the antiderivative with b substituted in, so we'll get b squared on 2 plus b. Subtract away the antiderivative with 0 substituted in, which is simply 0. And now we're going to multiply every single term by 2, so that we don't have any fractions. So we're going to have b squared plus 2b is equal to 15. So therefore, b squared plus 2b minus 15 would equal 0. So now that we have the quadratic equation equal to 0, we can factorise and use the null factor law. So we're going to factorise by looking for the factors of negative 15 that add up to 2. So we're going to have b, and it's going to be plus 5, and b subtract 3 is equal to 0. So therefore, b could equal negative 5, or b could equal 3 are possible values of b. However, we know that b must sit between 0 and 4, so that we get an area under that curve as being 5 on 8. So therefore, b equals 3 is the only answer to this question. So from the examiner's report, we can see that 45% of students got full 3 marks for this question, and that poor anti-differentiation brought on by the presence of the denominator of 12 meant an unhelpful start for many students. And we overcame that particular issue on the previous slide by taking the common factor of 1/12 outside the integral. Obtaining and solving a quadratic equation was fundamental to further progress in this question, and students are reminded that the quadratic formula and the null factor law and factorisation can only be used if the quadratic is equated to 0. A number of students established a quadratic that was not equal to 0 and used guesswork to obtain one possible solution for their quadratic. Alternatively, there was a geometric approach that could have been used. A few students used a mixture of triangles and rectangles, or trapezia, to find the area where it became 5 over 8 square units.